Dear friends, right now let's try to solve this problem number 3. A rod of length L made up of two halves hangs on two ropes of length L as well, and what angle does it make with the horizontal when in equilibrium if the halves are made of the materials of density rho and 2 rho, double rho, right? Well, this problem says we have some material, some object which is made of two materials. This half of our object is made of different material, and this half is made of different material. That's why their density is going to be different. Okay, and also it is said that we have the length of these rods as L and the length of the ropes which hold this rod are L as well. Okay, so basically what it means something like this. This is a very good hint to us that all three sides are the same length. It means that all three sides are the same angle. This is theta, yeah, this is also some theta, and this is also some theta, right? But we know that any triangle has got to be 180 degrees, and if we have three equal angles, yeah, theta plus theta plus theta will be just 3 theta equals 180 degrees, which means that theta is just 180 divided by 3, just 60 degrees. That's why let me just take these thetas off and let me write them as 60 degrees each. Okay, yeah. What angle does it make with the horizontal when in equilibrium? Yeah, so this thing, what we need to find is about angle alpha, right? So what we need to find out this angle alpha. Okay, good. This thing is what we need to find, and of course we can apply here this law of z, which we have told about, and this thing is z, as you can see, and if this angle is alpha, this angle is alpha as well. We know that from geometry. We don't have to prove it and waste our time. Okay, so this thing, this alpha, cannot be just some 30, for example. Why? Because this thing is not straight. This line is not straight. It does not stand like this. That's why if this part is 60, that part is 30. No, it does not work like that. We don't know what is the angle between these two, and we don't have to waste time on that. Another important thing to note is that as this is the rho of object 1 and this is the rho of object 2, yeah, let me write them as this is density of object 1, this is density of object 2, and let me write them as this one. Density of object 1 is just rho, density of object 2 is double rho. What about the masses? Well, we know that rho has a formula as m divided by v. If I move v there, it's got to be just mass equals rho multiplied volume, right? And if I want to find mass of object number 1 and mass of object number 2, it's got to be just for mass 1, it will be just rho 1, volume 1. This would be just density of 2, volume 2. But the volume 1 and volume 2 are equal. Let them call just some v. Why? Because it's just two halves of the same object, yeah? That's why their volumes are the same. They are just two halves, 50%, 50%. That's why it's going to be just density of number 1 would be just rho multiplied the volume. This thing's got to be double rho, which we have written just right here, and the volume is again just the volume. And if I want to find a relationship between m1, m2, this got to be rho v. This is just 2 rho v. As you can see, this thing cancels out, and if I move 2 there, it's got to be just mass 2 is double of mass 1. Yeah, so basically, if I call just mass of mass 1 just m, it means that mass of mass 2 would be just double m. Yeah, that's why let us write it somewhere here. Just this is m, this is double m. Yeah, that would be good. This is just a short proof why their masses are double in difference. Yeah. Okay, as this is the problem about torque, it means that there are forces which are trying to rotate this thing. In fact, we can note them like this. This is our tension number 1. This is our tension number 2. This one, tension number 2. Also, we've got non-uniform mass in this object because the one half is double the weight of the other half, which means that the center of mass would probably be here, but in physics we don't guess. We are trying to solve problems. That's why instead let me treat them as two separate objects. Yeah, this thing has its own mg. This thing has its own mg, which is just a double mg because we have proven that this is just double m. Okay, we can do it as long as the logic is correct and the maths is correct. And right now we need to write equations on torque. Yep. Equations on torque would look like this. If I just put this object horizontally, perfectly horizontally, like this, let's imagine it. Let's try to imagine. This is two halves. This tension looks somewhere here. Tension number 1. This tension number 2 looks a little bit here, probably. Also, in perspective, if we put this object perfectly horizontally, then these two weights look somewhere there. This is mg, this is double mg. Why this is important? Because we know the formula of torque. Yeah, this is just torque equals force cross product r. Cross product means the force which is trying to rotate must be in some distance from the pivot, and it must be perpendicular to that distance. Also, we know that this is equilibrium state. Yeah, this is stationary state. That's why the sum of torques is going to be just 0. Okay, we need to take only perpendicular components, and we know this is 60 degrees as we have discussed before. Yeah, the angle, even if we rotated the rod, the angle between tension force and rod does not change. It is just 60. The same thing goes for this one. This is just 60, and the vertical component, which is this one, yeah, this would be tension 1 sine, because it's opposite sine 60 degrees. Yeah, this one. The same thing goes for this one. In fact, it's just tension 2 sine. It is opposite 60 degrees. Okay, let me not open it right now. Yeah, let me work with this one. Okay, what about this situation? Well, we have what? We have this kind of floor, and this is our angle. Yeah, this is our angle. And, well, the image is not correct. In fact, this thing has to be just 90 degrees because, as you can see in this image, it makes 90 degrees with the floor, and that thing that I've drawn is just a little mistake. But you get the concept. Yeah, you get the concept. If this is our angle alpha, which we have noted, this is 90 degrees, this has got to be 90 minus alpha. Then this thing's got to be alpha as well. That's why, let me just put alpha right here, and the same thing goes for this. It is the very same principle. This will be alpha, which means that this component, this one, it's going to be mg, double mg, I'm sorry, double mg, cosine, because it's adjacent, cosine alpha. This thing is going to be mg cosine alpha. Okay, good. Right now we know the forces which are trying to rotate. Yeah, not all the forces. For example, the horizontal components of this tension 1 and tension 2 cannot rotate. They just can pull. Yeah. Okay. And the same thing goes for weights. Not the entire weights can rotate. They just can pull, but their components can rotate. They're perpendicular components. Okay, that's good. Right now, let's select some pivot. Yeah, let's put it, I don't know, just somewhere here. And then it means what? It means that tension 1 sine alpha, sine 60 is going to cancel out. Why? Because we know this formula. Force cross product r, it must be some distance. But yeah, let's not step too soon. Why? Because in this case, let me take 2 copies of it, because I will explain you why a little bit later. Let me take this thing and copy it somewhere here. We'll need that. Yeah, we will need that. Okay, this is the first case. Let me choose some red, or I don't know, like orange. Yeah. From this perspective, tension 1 is trying to rotate somewhere here. Tension 1, mg is trying to rotate there. Tension 2. Oh, okay, torque 2 is going to be, okay, here, let's say. This is our torque 2. Let's name it torque 3. Let's name this thing torque 4. Yeah. And if we write equations for this image, yeah, let me take those 2 images a little bit somewhere there, because it will be important to us a little bit later. You will see why. Yeah. In this case, we've got what? Tension 1 and tension 4 are trying to rotate. Well, tension 1, 3, 4 are trying to rotate this thing. But in fact, I would say this tension 1 does not, torque 1, I'm sorry, not tension, torque 1, it doesn't even exist. Why? Because this thing cannot rotate, in fact. This thing is 0 distance, but yeah, just for formality, let's write it. Let's write it. It must not even have a direction, but let's write it down. Yeah, why not? Torque 1, 3, 4 are trying to rotate it clockwise, and torque 2 counterclockwise, and it does its job very well, because this thing is not being rotated. That's why, let me write it something like this. Torque 1, torque 3, and torque 4 are clockwise, minus torque 2, it is 0. And if I move torque 2 there, it's got to be just like this. This got to be just equal. If I open up, yeah, this torque 1's component is just T1 sine 60. T1 sine 60 degrees. But it's r, this is the force in this formula, but its distance from the pivot is just 0. That's why it's going to just cancel out. For torque 3, it's going to be something like mg cosine alpha. And this is the most interesting moment. Mg cosine alpha. And right now, let's work with this. Let's give some meaning to all of them. I would say, as we have chosen the center of mass for each object separately, we know that right now it is divided into 4 halves, because we have 2 halves, and then we have chosen the centers of those halves. That's why right now each side is just 25%, but we don't know the entire length. We just know it is just L. We don't know the value, but let us give this part length x. This is going to be x as well, this one and this one. Yeah, pretty good. It means that our mg cosine alpha is just x distance away from the pivot. It is just x. Or we can just call it L divided by 4, but it's not, well, let's not make our life even harder. Let's just make it x. What about torque 4? It is double mg cosine alpha, and it is 3x's away from the pivot, as you can see. So it's going to be plus double mg cosine alpha, and this is going to be 3x. Okay, that's good. Well, we can just cancel this thing out. We don't need that. What about torque 2? It's just t sine 60, and it is the entire length. Let's call it 4x. Yeah, this is t sine 60 degrees, 4x. Yeah, and right now what we can do, we can see that this is x mg cosine alpha. Right here we have 6 mg cosine alpha multiplied by x. So that's why it's going to be what? This thing's going to be 7. Why? Because this thing is 1, this thing is 6. Yeah, it's the very same thing. 7 mg cosine alpha x multiplied equals t sine 60 multiplied by 4x. We can just cancel out those x's. In fact, those two are not important anymore, and we can see this tendency. Yep. Okay, this is pretty good. What about the lower one? Let's work with that as well. Let me choose this image, put it somewhere here, and then let me select another pivot. Yeah, the second pivot. Why? Because if we put something like this, it would be pretty convenient to us, in fact. And you'll see that. In this case, let's put our pivot somewhere here. And then you see that mathematically, it would not be a problem, and it would be even very comfortable to us. This will be x, 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 and x as well. Okay, in this case, right now, our tension 2 sine 60 degrees is 0 distance away from the pivot. Let me choose this thing, just copy it, because it's going to be something very close to it, but you will see one more interesting thing. From this case, from this perspective, this is the torque 2, this is just torque 1, yeah, this is trying to torque 1. But if you look at here, this torque 3 has changed its direction. This thing also has changed its direction. That's why it's even interesting. You can see that tension 1 is trying to rotate it clockwise, and all the others are trying to rotate it counterclockwise, which means that tension 1 minus all those things, this is minus, minus, and it has to be something like this. This is, this is minus, minus, minus. It's equilibrium, it's just 0. But if I move all of them to another side, it's got to be just plus. Yeah, it's got to be something like this. It's got to be equal plus plus. Yeah, good, good. For tension 1, right now, it's not 0 distance away. This is going to be equal sign. Yeah, well, the only thing that has changed, not the forces are the same. They're distances from the pivot, because we have changed the pivot, right? For tension 1, the distance is 4x right now. Right now, this distance is 4x. Yeah, let me move it a little bit further. Yep. For torque 3, it's going to be mg cosine alpha, but right now you can see it 3x is away from another pivot. So it is just 3x. What about 2 mg cosine alpha? It's just 1x away. That's why it's going to be just x. And this is going to be plus t2 sine alpha. Yeah, let me choose it somewhere here. T2. It's just 0 distance away. You can see it, it's just on the pivot. That's why this thing is going to just cancel out. This thing is not important to us. And yeah, let me just take this out, and you'll see one more interesting thing. This would be just still T1 sine 60 degrees multiplied 4x equals. As you can see here, it's just 3 mg cosine alpha x. This is 2 mg cosine alpha x. That's why this will be 5 mg cosine alpha x. And we can cancel these x's out, and you will see this tendency again. Okay, good. Okay, so yeah, this is just tension 2. This is tension 2. This is tension 1. This is tension 1. Okay, good. Okay, we need to find this angle alpha. What we need to find is this alpha. Good. Can we just take these things, these two equations, and put them together, equalify? Well, probably, but this thing would not be enough. Why? Because we have this alpha unknown. We don't know the meaning of tension 2. We also don't know the meaning of tension 1, right? So there are 3 unknowns, but instead, what we can do is dynamics. Yeah. Right now we can write down the relationship between tension forces, and then we will see what will happen. Well, how do we write equations for tensions? Well, I need to find out this totally horizontal component of tension 1 and totally horizontal component of tension 2. Yeah, this is going to be, let me choose green. This will be tension 1, some sine, cosine, does not matter right now. This is tension 1, I'm so sorry. This is tension 1. Tension 1. this is tension 2 sine or cosine. We'll see about that. So what we have, we need to find this angle in order to put that totally horizontally. Yeah, we cannot apply just 60 degrees because it would be this component along the rod, but we don't need that. We need just this horizontal one. Well, as you can see, if this entire length, yeah, let me choose some visible, well, yellow, okay. If this entire side is 60 and this is just alpha, this thing's got to be 60 minus alpha, right? 60 minus alpha. Why? Because 60 minus alpha plus alpha just gives us 60 degrees. It's correct. Okay, this thing is 60 minus alpha. What about this one? Well, if this length is 60 and this is alpha, it means that this entire side, yeah, this entire side, this one, is going to be 60 plus alpha. Yeah, it's pretty feasible. You can see it. So let me choose this angle. This would be 60 plus alpha. Okay, right now it's good. And definitely it is adjacent, it is touching. That's why it's got to be tension 1 cosine, but not just alpha, it's 60 plus, not 60 minus alpha. This is t cosine 60 plus alpha. Yeah, good, good. And we see that there is no any other force acting on our horizontal axis, right? Those two are trying to move this object different directions, two different opposing directions, and this thing is not moving, it is in equilibrium. That's why it means that these two are just equal to each other. Yeah, we just write here, yeah, let me choose this one. Sum of forces equals 0. So tension 1 cosine 60 minus alpha equals tension 2 cosine 60 plus alpha. Yeah, why? Because in fact it must be just minus in here, and it's got to be just 0 as in this formula, but I already moved it here, and that's why it became just positive. Okay, it's got to be just it's got to be just equal sign. Okay, from here we can just find the relationship between t1 to t2, and it's got to be just cosine 60 plus alpha, and here this thing got to be cosine 60 minus alpha. These two things are pretty similar in fact, but if I open this up, it's going to be cosine 60 degrees cosine alpha plus going to be minus, and this is sine 60 degrees sine alpha. You know this formula from trigonometry, and below it's going to be totally the same thing. In fact, it does not change, but this sign, if it is minus, instead is going to turn into plus. Okay, so we know that tension 1, well, tension 2, I can write it like this. Tension 2 is 7 mg cosine alpha divided by 4. Good. Here I can write what? Tension 1 is going to be, okay, didn't I forget? Yeah, I've forgotten this thing. Yeah, I'm truly sorry. This is going to be 4 sine 60. Yeah. Sine 60 degrees. This must not be forgotten. The same thing goes for here. 5 mg cosine alpha divided by 4 sine 60. 4 sine 60 degrees. Okay, if I put them inside here, yeah, let me just choose tension 1, which is here. Yeah, choose tension 2, which is here. Yeah, and as you can see, the tension 1 and tension 2 are divided by each other. This thing is going to just cancel out. This thing is not important. I would put something dividing symbol like this, and you can see that this thing is going to cancel out. This thing is going to cancel out. Mg cosine, yeah, this thing is not much important. 5 divided by 7, yeah, their relation. Yeah, this is just tension 1 divided by tension 2. Yeah, this equals, yeah, and you can see that their relation is just 5 divided by 7. Okay, and their relation is also this thing, this long thing, but we can put there some numbers. Yeah, well, those numbers got to be cosine 60 is just 1 divided by 2. This is just 1 divided by 2 cosine alpha minus this thing is square root 3 divided by 2 sine alpha divided by this is going to be the very same thing, cosine alpha plus square root 3 divided by 2 sine alpha. The only difference is just that plus sign. And if I just move, multiply this thing into this, multiply this one into this, it's got to be just what? Well, in fact, this thing's got to be 5 multiplied 2 below. Yeah, so it's got to be just 5, 1, no, this is cosine alpha minus square root 3 sine alpha divided by 2, and we can just move the 2 outside the brackets. Yeah, this thing's going to be just 5 divided by 2. Yeah, this is in brackets. The same thing goes for the other side, in fact, the very same thing. But this is going to be plus, yeah, because this one, the plus sign is multiplied to that. And this thing's going to be just 7 divided by 2. 7 divided by 2, this is going to be cosine sign. Cosine alpha minus square root 3 sine alpha. Yeah, pretty good. And if I just open these up, yeah, it's gonna be what? Let me just open these brackets like this, not writing all of them again and again and again. Instead, cosine alpha will be just touching like this. 5 multiplied 2 just multiplies that thing again, and the same thing goes in here. This thing multiplied 5. Oops, this minus sign. 7 divided by 2 multiplies to that thing again. And if I move cosines to one side, it's gotta be just let me instead, if I move sines, sine alpha, let me choose red. If I move it here, and if I move cosine into that side, it's going to be something very interesting. It's going to be just 5 square root 3 divided by 2 sine alpha, plus 7 square root 3 divided by 2 sine alpha. This side, we will have 7 divided by 2 cosine alpha minus 5 divided by 2 cosine alpha, and again, sine alpha. Okay, let me write it somewhere here. Let me choose it. This is very important because we are still, we are already there at the very end of this problem. You can see that the sine alpha is just a common factor. This would be sine. Oops. Okay. Yeah. So you can see that sine alpha is just a common factor, and 5 square root 3 divided by 2 plus 7 square root 3 divided by 2. Here we have cosine alpha, which is common factor, and this thing's got to be just 7 divided by 2 minus 5 divided by 2. And if I just move cosines into that side and this thing into this side, this is going to be just sine divided by cosine, which is tangent cosine alpha. And here, above what we have, this thing is going to be just 7 minus 5 divided by 2. It's going to be just 2 divided by 2. It's just 1. It's just 1. Above, we will have just 1. Okay. What about this thing? It's got to be 5 square root 3 plus 7 square root 3 divided by 2. And square root 3 is common factor, which is square root 3. 5 plus 7 is 12 divided by 2. This thing's going to cancel. And this will be just 6 square root 3. And below, we will have 6 square root 3. And this would be tangent alpha equals, and if I just multiply it, square root 3, well, like this, to not leave any square root under, this thing's going to be what's above what we have is square root 3 divided by, well, this thing's is going to be just become a regular 3 multiplied to 6. It would be just 18. This is our answer for our case, our problem. We were meant to find that alpha, and we have found it. This angle alpha is now found. This thing's going to be just arc tangent square root 3 divided by 18. In fact, if I calculate it, should I? Yeah, let's try. Why not? If I want to calculate it, for arctangent, square root 3 divided by 18, it's going to be some angle like 5.5 degrees. Yeah, pretty good. This is going to be just 5.5 degrees. Okay. Yeah, good, pretty good. I like it. This is our answer. Yeah, this is our answer. This is our physical answer. This is our mathematical answer. Okay. Good. So, yeah, a little bit long. We have chosen 2 pivots, but it's the most convenient way because we can divide them by x distances, which is pretty good. It's pretty convenient. And, yeah, the rest is just the math. The physics has ended right here. The rest is totally just the math, and this is our answer. I hope that everything was clear, but if you have any questions, you can write me privately. Please be free, and goodbye. Thanks for your attention.